Good evening, everyone. Welcome back to NPTEL live session for week 10. So we'll be shortly starting up the list session, maybe at after 2-3 minutes, once everybody will be joining. Okay. So in last live session, we had discussed a lot of concepts. For example, isomeric shift. Second concept, we had quadrupole splitting and electric field gradient. And during that, we solved a lot of questions also as an assignment problem. And one was as homework. So I hope you guys have at least tried it, and we'll now solve it over here. Let's see the what comes to be the right answer. So just to give you a brief before we start solving this question. So delta EQ is defined as quadrupole splitting. Okay. So we know that for delta EQ to be non-zero or to be existent, we need to have electric field gradient non-zero. And for this, two factors are there. First is lattice contribution, and second factor is valence contribution. So we already understood this concept in the last lecture, where lattice contribution means we are talking about the coordination geometry say if all the ligands, this is a ligand which is surrounding the metal, and if it is in pure octahedral geometry, all ligands are same. That means there is no asymmetry. That means lattice contribution would be zero. Or if we have other than octahedral geometry that would be having different shapes or geometries, that at that time lattice contribution would be counted. Second of all, if we consider Jahn-Toller distortion, whenever we have a higher symmetry, that means octahedral symmetry, we come from octahedral symmetry to lowering it down. Like its symmetry has been lowered, that is called as Jahn-Toller distortion. And for this, we need to have unsymmetrical distribution, electronical distribution in T2G, most prominently in EG, but if not, then T2G unsymmetrically filled also would be giving us weak Jahn-Toller distortion. And whenever there is a distortion, that means we are moving from symmetry to asymmetry. So that will also contribute to the lattice contribution parameter. And third parameter would be like out of all ligands, all 6 ligands, if we are taking an octahedral case, 5 are of one type, say for example L, and 1 is M. Or if you'll say for example X. So all 5 would be, say for example, we are taking water. All the 5 ligands are water and 1 ligand is chlorine. So that octahedral geometry is no longer an octahedral completely, because now the one ligand has been replaced by chlorine. So that asymmetry has come. There is no more symmetry present, and that parameter also will give you a contribution of as a lattice contribution parameter. I hope this is clear. Is there any confusion regarding this?
No confusion, ma'am.
Okay. So the second parameter that we looked into, that was valence contribution. And valence contribution is something which we are talking about the how the valence electrons, the d electrons are being filled in its d orbitals. So if we have symmetrically filled T2G and EG, then it is having no valence contribution. Whereas if it is unsymmetrically filled, we'll be having valence contribution. So those two parameters have to be kept in mind whenever we are talking about quadruple splitting. So the question says, assign the delta EQ values 0, the value is 0, 3.4 and 1.85 millimeter per second for first complex, iron aqua complex. B is iron CN4, CN6 4 positive, C is RnNO, CN5 2 positive. So in this particular case, we'll firstly take up so firstly we have iron aqua 2 positive. Second one we are having iron CN6 4 negative. And third one that we have is iron NO CN whole 5. It is 2 negative. Okay. So firstly we'll check their oxidation state. So here iron is, water is a neutral ligand. So iron is in +2 oxidation state. We have already seen how to calculate the oxidation state. if I'm taking its oxidation state as X, iron will not contribute to any, it is not having any charge, so it's 0 and +2, so it becomes iron in +2. Here also X, Cn is -1 charge into 6 -4, X becomes +2. Here also, whenever nitro group is connected with iron, it will always give you a positive charge. So it becomes +1, -5, -2, that is -2 + 4, that is also iron in +2 oxidation state, right? So when we have all iron in +2 oxidation state, we know that D6 electrons would be there as per its electronic configuration. So D6 electrons are there. We're not talking about the isomeric shift over here. We are only focusing on whether something is giving quadrupole splitting also, or how much value it would be, which one is going to be more prominent, which one is going to be less prominent. So firstly, we will see the lattice contribution in case of iron. So in case of iron, if you'll see the geometry around the iron, here is one water molecule. Right. So firstly, say lattice contribution. So iron is surrounded by 6 water ligands that are same. So from that particular geometry, it is not going to have any kind of lattice contribution. But check whether it is having a valent Jahn-Torr distortion or not. For Jahn-Torr distortion, we need to see its how it is being filled. So we know in octahedral field we have, since it is, and also we have to first check whether water is a strong ligand or a weak ligand. It's a weak ligand, so it will make a high spin complex. So D6 high spin would be filled like this particular way. Firstly, all the orbitals would be filled with 1 electron, and the last electron will go to T2G. Now, tell me that whether there would be a chances of any Jahn-Torr distortion to be happening in this particular case or not.
Jahn-Torr distortion available, ma'am.
Yeah, because our T2G is symmetrically, it is filled unsymmetrically. There is like one orbital is being filled by 2 electrons, others are 1-1. So this is a case of Jahn-Torr distortion, though it is weak, because if we are having unsymmetrical nature in EG orbital, that would be having more Jahn-Torr distortion parameter compared to the T2G, because EG orbitals, they are more that orbitals, the ligand orbitals, they are more in connection with the metal. They can approach more. So the metal orbitals and the ligand orbitals, they feel more repulsion over there and energy becomes high. And there we have the more parameter of JTB. And say, for example, if we have two cases, one case there is T2G unsymmetrically filled, other case EG is unsymmetrically filled. So which one is going to have more Jahn-Torr distortion parameter? That is the one which is having unsymmetrically filling of the EG orbitals, that is going to have more or strong JTD. And that strong JTD could also be a factor for giving you more quadrupole splitting, right? So that we'll see later. So in this case, Jahn-Torr distortion is occurring, which is leading to, okay, there is lattice contribution is there coming from Jahn-Torr distortion. Now, when we draw this kind of electronic configuration and the splitting of the electrons in d orbitals, we can see easily that there is unsymmetrical filling of the electrons. So therefore, valence contribution is also there. When both the parameters JTD, that lattice contribution and valence contribution is there, that means electric field gradient is non-zero. Therefore, we would be having a quadrupole splitting. So that would be non-zero. We're not talking with the values right now. We are just saying whether it is existing or not. So is that clear?
Clear, ma'am.
Okay. Now we'll go to the second case, which is iron cyanide complex. Firstly, we got to know that it is also having iron in +2. Second thing, before going to the electronic configuration and the distribution of that d electrons, we need to see whether it is of the ligand Cn negative, it is strong field or it is weak field ligand, and whether it is going to make high spin complex or low spin complex. So first question, Cn negative, the cyanide ligand is strong field or a weak field ligand?
Strong field ligand, ma'am.
Yeah, because it's a
Low
pi
spin
acceptor.
complex.
So it will form a low spin complex. So we got to know iron in +2, low spin. That means D6 low spin. Whenever there is low spin complexes, what happens? Pairing of all the electron happens. So we would be having this kind of, that is energy. It's Eg orbital, T2g orbital. Now start filling up here. So firstly, it will get paired up. So T2g6, Eg0. Now tell me whether it is having any lattice contribution. Firstly, lattice contribution, see the number of ligands, whether they are same or different. All are same in octahedral, so that is not giving any lattice contribution. Secondly, whether there is any possibility of Jahn-Teller distortion. So since there is no unsymmetrical filling of the electrons in T2g or Eg, therefore there is no lattice contribution because no JTD is also there. Is that clear?
Clear, ma'am.
Yeah. Now, similarly, looking at this, can you please tell me whether it is having valence contribution or not?
Valency contribution not available, ma'am.
Yeah, because there also we have to see the same feature, whether T2g and EG are unsymmetrically filled. Since it is symmetrically filled, so we don't have a valence contribution. Now, both the parameters, lattice as well as valence, they are not existing in this particular case. Therefore, that electric field gradient is equals to 0 and delta EQ is equals to 0. Is this clear?
Clear, ma'am.
So out of the three options, okay, we have found out that this 0 value is existing for option B. Is
B
it clear?
complex.
Yeah. Now we'll see the third complex. I'll draw it in the second page. Now we have third complex, iron, NO, Cn, whole 5, 2 negative. Here also iron is in +2 oxidation state. Now you need to tell me NO and Cn. Are they strong field ligands or the weak field ligands?
Strong field ligand.
Right. So they both are strong field ligands and therefore they will make low spin complex. So in this case also, iron in +2, that is D6, it is going to make low spin, right? So firstly, we will draw its filling of the electrons. Since it is low spin, it is going to paired in that T2g orbital itself. So T2g6, Eg0. Now you tell me, is there any valence contribution here?
Valency contribution is not available in this case, ma'am.
Yeah. So valence contribution is not there because no unsymmetrical filling. Now tell me whether there is Jahn-Teller distortion.
Not available, ma'am.
Yeah, because same reason, and there is no unsymmetrical filling, so Jahn-Teller distortion is also not there. So do you think there is any lattice contribution over here?
Lattice contribution available, ma'am.
Why is
Because
it?
there are two types of ligand is available.
Right. So still we have lattice contribution, though it is weak, but it is there because we have one ligand is NO and other type of ligands are CN. So when two different types of ligands are we having, or it could be three different types of ligands. So in that particular case also, we are not maintaining the octahedral geometry, like, which is completely symmetrical. So therefore we have no valence contribution, but we have lattice contribution. Therefore, EFG is still not 0 and delta EQ will exist. Now the main question that we have, just to brief you, in case of complex A, both lattice contribution and valence contribution existing. In complex B, none of the two existing. And in complex C, only one factor, that is lattice contribution existing. So therefore, we are now comparing A, B, and C. The values that are being given as 0, 3.4, and 1.85. We have to assign these values to all three of these complexes. To positive, iron CN6, O negative, iron NO, CN5, 2 negative. Okay. So here we saw that lattice contribution, valence contribution existing. Here lattice contribution is not there. Valence is also not there. Lattice is there. Valence is not. So we have given the delta EQ value was found to be 0 over here. That is clear. Okay. So this value can be assigned to complex B. Now you tell me which one is going to have more delta EQ out of A and C.
A option, A complex are having more del EQ value compared than C, ma'am.
Why is it so?
Because both lattice contribution and valence contribution is available in A complex. In C complex, only having a lattice contribution, there is no valence contribution.
Right. So when both the parameters are available, so therefore it is having more delta EQ value. There is only one parameter available. So now we can assign A is having more delta EQ compared to B, C, and
Ma'am, I have one doubt.
Yeah.
In A complex, H2O ligand is available, same ligand. Why we are called as lattice contribution is available?
Because we saw here that Jahn-Teller distortion is there. So in lattice contribution, we have to consider both the factors. I told you, right? Firstly, you saw whether ligands are different or not. If ligands are different, that
Okay,
means
ma'am. Okay, I understood.
Yeah. In the third case, we were not having Jahn-Teller distortion, but still it was lattice contribution as the ligands are different. When ligands are different, that time also it will give you contribution from the lattice, or if it is coming from the any kind of distortion, that will also contribute as a lattice. So is that clear now?
Clear, ma'am.
Okay. So now this A can be given a value of 3.4. This can be given a value of 1.85 and B is 0 because there is no splitting. So now this question is clear?
Clear, ma'am.
Okay. Now we will go to the main topic of our today's lecture. So here are the assignment problems that we'll be taking up this time, but at the end. So today's lecture is also a continuation of what we have seen in week 9 lecture. That means we discussed about a brief. I'll give you about the mass power, isomeric shift, electric field gradient, quadruple splitting, and many more other examples are there, which will let you to understand more about what kind of ligands are there, how the splitting will happen, how do we have to look for which one is going to give you more delta EQ value or something. So here, firstly, I'll just brief you a bit about what we have learned so far in mass power spectroscopy. So we have seen that mass power spectroscopy is related to gamma rays emission and absorption. So here we have a prerequisite of source and the sample to be same. For recoilless energy, we have kept them on a solid matrix which restricts their motion, and therefore there is very minimal recoil energy loss. And to have a proper spectra where we could see where the detector could see the gamma rays to be emitting out, we need to be considered the Doppler effect, where in Doppler effect we could move the source away or towards the sample. See here, we have source. Both the source and sample are same. Firstly, we have kept them in a solid matrix. So this box we are representing as a solid matrix. And here is our detector. And this one has been, earlier they were fixed. So this was fixed. This is also fixed. But this one is movable. This is your source. This is your sample. And this is your detector. So the main aim is, if it moves towards the sample, that is moving with a positive velocity. If it is moving away from the sample, that is a negative velocity. And with respect to that only, whatever the radiations which are transmitted, that would be detected by the detector. And therefore, we will be ending up having a plot between transmittance and the velocity, because it is millimeter per second with velocity. It is moving, the source is moving. So we can possibly be having this kind of spectra where we can have, if it is not at all moving, the earlier case where we have kept it in a solid matrix, it is not moving. So V is equals to 0. If it is moving towards the sample, that means if it is moving towards a sample, there would be some common area which has been absorbed and rested off has been transmitted. So the transmitted radiation would be this value. We can have V1. And similarly, if it moves beyond its range, like totally it is going away from it. For example, here is my, this is my sample. This is my sample. And the source has completely gone to this level here. It has gone towards this direction and not at all, there is no matching of the absorbance or whatever it is there. So when this is a particular case, there is no common absorbance value. So if there is no common absorbance, that would be giving you 100% transmittance. So if I'm marking it as 100%, so it will come as a V2 over here. So this plot is very important to comprehend. Similarly, if we go in opposite direction, it would be -1 and it would be -2. So when we are making or making a line or joining all the dots, we are getting this kind of curve. And this is actually your Mossbar spectra looks like. Right? So after that, what we have, then we talked about isomer shift. And that comes from the movement of your source towards the sample. So what difference it would make? Either it would move towards a more positive side. Say, for example, if I'm having here, and if one plot is here, the second complex is going here, and the third is moving here. So if this is my delta, this is delta 1, this is delta 2. So delta 1 is more positive compared to delta. Delta 2 is more negative compared to the delta or delta 1 also. So how we see that shift is going to happen from its original position. So that depends upon the two factors. Firstly, this delta depends upon the sign of your delta R by R, where delta R is nothing but the difference of radius in the excited state and the radius of the nucleus in the ground state. And in case of iron 57 nuclei, we know that radius of the excited state nucleus is less than radius of the ground state nucleus. Therefore, delta R is a negative value. So this sign is negative. And it is also dependent on the electron density, that S electron density, which is going to penetrate into the nucleus. Penetrating into the nucleus. And this factor is actually dependent on the amount of d electrons is there, or we call it as a shielding effect. Say, for example, if I have a nucleus over here and it is S electrons are outside and D electrons are here, they will try to shield the S electrons from the nucleus. That means it will not let more number of D electrons, will shield more the S electron density to get into the nucleus. So therefore, if we have more D electrons, it would be giving more shielding to the S electrons. Therefore, this chi-square value would be less. If this is less, and as total, we have delta minus, and this value is less, so this would be less negative. Whereas if we have so one factor is more oxidation state of the metal, that would be having less D electrons. If D electrons are less, that means shielding effect is going to be less shielding effect, therefore more chi-square. This is the probability of S electron density. This will give you more negative delta. Otherwise, if we have less oxidation state or more D electrons, it will be having more shielding effect. That will give you less penetration of the S electrons into the nucleus, therefore less delta negative. So these are the relative values. So when I said that delta is here and other peak is here, delta 1, and second one is delta 2. So delta 1 is more positive compared to delta, which is more positive means it would be less negative. That means here the delta 1 would be corresponding to that complex which is having iron in less oxidation state, and vice versa for the delta 2. So this concept is clear?
Clear, ma'am.
Okay. So after that, we moved that earlier we were having a monopole kind of situation where only nucleus is there and we have electron density around it. So that is happening when we are considering we have a spherical nucleus. And spherical nucleus corresponds to I equals to half or 0. That is the condition for the spherical nucleus, and we consider the radius from the nucleus is r. If at all we don't have a spherical nucleus, we have a non-spherical nucleus. So in that particular case, I value has to be greater than half. In this particular case, now we will be having an ellipse kind of shape of the nucleus where the charges would be on the end and the electrons would be surrounding like this. This would be comprising of a quadrupole. Quad means 4, so it is a quadrupole, and that where we consider the terminology as electric field gradient. So this electric field gradient happens when we have non-spherical nucleus and there is some kind of quadrupole is existing. And we talked about the delta EQ, which is a quadrupole splitting. Also, in this particular case, we saw that non-spherical nucleus has to be there. And here we talked about the lattice contribution and the valence contribution. In lattice contribution, we have seen that in lattice contribution, we have already considered two factors. Firstly, ligands are same or different. And Jahn-Teller distortion, that's a octahedral symmetry we are talking about. And valence contribution is the unsymmetrical filling of d electrons in d orbitals. So these parameters will let you have a, so for example, we have this transmittance and velocity graph, and earlier one complex is, say for example, we were taking this iron water. Just now we saw this example and we got to know that both lattice contribution as well as valence contribution was existing. Therefore, delta EQ would be there. And if I have a certain value of this delta, this isomeric shift is there, certain value is there. And because of this lattice contribution and valence contribution, this will get split into two halves. So now the main spectra will look like this particular way, where delta EQ, we found it to be 3.4 mm per second. So this value is nothing but the difference of your delta 1 minus delta 2, that will give you delta EQ, and isomeric shift you can get as an average of these two. So this particular way we see that, okay, how the splitting is going to occur. So here the question is like, why are we splitting that one peak into two? Because we saw in case of iron 57, we have two main states. One is 3/2, other is 1/2. That's ground state. This is excited state. So out of the two, which one is having a non-spherical nucleus? Is it ground state or is it excited?
The excited state, ma'am, 3/2.
So that excited state in presence of the electric field goes like 3/2. That splitting happens and this remains as plus 1/2. So here this now the transition is going to happen like this way. Earlier the transition was only this way, one. Now it is split into two. That's why one peak we see to split into two peaks. Right? So if there is multiple states over there, then depending on the transition happening, there would be different number of peaks present in that particular complex. So up till this point, is it clear? Like whatever we have seen, and then we can start with the new examples for this lecture. Or any doubt is there?
Ma'am, I have one doubt. In last assignment, one question is available.
Yeah.
That is, which of the following will have the highest isomer shift value? Actually, Fe, F2, that is the A option. FeCl2, that is B option. C option is FeBr2. D option is FeI2.
So is that what we considered it in the assignment, or it was in that course assignment you're talking about? Hello?
Ma'am?
Did we consider this one in our course, this one assignment, or you're talking about the course assignment? Okay.
Ma'am, in assignment having one question. That is which one of the following have higher isomer shift value?
Okay.
Already we know there are 4 options available for each question. A option is FeF2, B option is FeCl2,